So in this video, we're going to finish up the concept of momentum and impulse by looking at the graphical approach to impulse. The graphical approach to impulse is generally going to be most beneficial when you're dealing with a situation where the force is not being applied uniformly, or that is to say that the force is not constant. That is extremely common. You can think of a lot of situations where the force would be constant. So for example, the thrust on a car, it might be constant, but it might not be. If I push a cart down the hallway, I might be applying a constant force. But more often than not, the forces that are applied to objects, they are not constant and they vary over time. They increase and they decrease over time. And so this is why a lot of the questions that you're being asked using impulse, it always asks you for the average force, because the force is varying. So all that you can get with the impulse formula, just to remind you, the impulse formula is F delta T. All we can get is the average force. But I couldn't tell you at any specific time what the actual force being applied was, because this equation doesn't allow me to know that. However, we have equipment which we can use to monitor the force that's being applied to an object, and so by using the graphical approach, we can calculate the impulse even when the force is being allowed to vary. So before we look at the varying forces, let's look at a simpler situation where the force is not being allowed to vary, so that you can sort of conceptually see how this graph will be used. So the graph that we would want to look at is, of course, a graph of F versus T. And if we had a constant force, that might look something like this. Here's the end of it. The force stops being applied. And so in this case, in order to come up with the impulse, what I would want to look at for this graph is the area, because F times delta T would be the vertical height, F times the base, which is delta T. So the impulse is represented in this graph by the area. The area of the graph tells us the impulse. Now in a situation like this, it's not really particularly helpful, because if I know what the force is and it's not changing, then I would just use the equation. There's really no reason to go to the graph in a very simple situation like this. Just a single force being applied at a steady rate over the entire length of the time that the force is being exerted. So where this idea of the graphical approach becomes much more useful is when we look at a situation where the force varies over time. And there's a lot of examples where that occurs, but some of the best come in sports. So for example, when somebody strikes a soccer ball, what happens to the soccer ball is that the soccer ball gets compressed. So when the person first makes contact, there's very little force. I'm just barely touching the ball right now, but as I push harder and harder on the ball, you can see the ball compressing. And right now I'm exerting quite a bit of force. And as the ball begins to move, the ball will then eventually will move faster than the person's foot, and the ball will begin to decompress as the force lessens. I'm barely pushing on the ball right now until the ball finally loses contact and then goes on its way. This is true in golf, tennis, cricket, when a football player kicks the football. Any situation where a ball is struck, it follows a similar pattern in which the force is almost nothing to begin with, but steadily increases, reaching a maximum when the ball is most compressed. And then as the ball decompresses, coming off of the foot or club or bat or whatever it is that's struck the ball, the force decreases until the force goes down to zero as the ball leaves the object. So we could create a very simple model and just assume that the force that is being applied is increasing steadily over time, a lot like the way a spring would work. As the spring stretches, as the distance of the spring stretches, the force is steadily increasing in a linear way. So if we use a very simple model, then we might imagine that the force increases to some maximum value. That's when the ball is most compressed. Then the ball begins to decompress until eventually it comes back down to zero. Okay, now in this situation, the area of the graph is still the impulse, but I can't calculate the area by just simply saying F delta T, because it's not a constant force. It's not a rectangle. This is the formula for the area of a rectangle, base times height. But now I don't have a rectangle, I have a triangle. So I need to be a little bit more thoughtful about thinking about how to modify that formula so that it will accommodate this situation. And there are sort of two important forces that I might think about. One obvious one would be this one. And this is the maximum force. Since this force steadily increased from 0 as it rose, that means that there is also another force that's exactly, in this situation, halfway down. And we would call this the average force. Okay, in this situation, a simple linear situation like this, there's a relationship between the maximum and the average, and that is that F average is equal to 1/2 of F max. Okay, and only works in this simple situation because the force rose in a steady manner. Okay, so there's two ways to think about calculating the area of this, because it will still be true that the area is the impulse. The area is still the impulse. So I could just, think of this as a triangle. That would be the most obvious thing to do. And so my formula for impulse would look like this. I'm going to modify it to address this particular shape. And the formula for that, for the area of a triangle, is 1/2 base times height. So that would be 1/2. The base is delta t. I'm going to write that over here. And then now I need to be really careful about when I'm not just going to say F, because you can see the force changes all the time. It's constantly changing force. So there is not one single force. I need to be really articulate and be very mindful of what specifically is the force that I need to plug in here. And in this case, I would plug in F max. Okay? Now, you could imagine a situation like this. So here's F average, and if you were to imagine taking the top portion of the triangle and taking this guy and rotating him around so that he filled in this guy, and turning this guy around so that he filled in this guy, what I would end up with is a rectangle. And that rectangle's dimensions would still be delta t, it would still have the same width, but the new height would be F average. Which should make sense, right? Because the average force in this simple situation is equal to 1/2 of the maximum force. So an alternative that I could use, and I've seen this on IB exams, and they want a specific answer. They would not give full credit if you said 1/2 F times delta t. You would not get full credit even if your answer was correct, because they want you to specify, to be very articulate about what is the force that you are going to plug in. And in this case, you either do 1/2 F max times delta t or F average times delta t. Not 1/2 F average, just F average, the average force. The average force being 1/2 of the maximum. In most cases, generally speaking, at the level of this course, you would see a simple model like this. The simple model where the force steadily increases, it's a linear increase in the force with respect to time, is most often how the problem is asked. However, in the real world, it doesn't usually look like this. That would actually be pretty uncommon to see a force steadily increase over time. The more typical So if we were to actually measure the force over time, it would be more likely to look like this. So this is a much more real-world example. The force in the beginning grows very slowly, but over time, as the ball becomes more and more compressed, the force is increasing very rapidly until it reaches its maximum value. And at that point, the ball is being pushed along. It cannot be compressed anymore, so the ball is just simply being pushed along, and then the ball begins to decompress as it comes away. Obviously, this is a little more challenging situation. We still obviously do have this value that we would call the the maximum force, but it's not as obvious where the average force would be. It could be in the middle. It's possible it's in the middle. It depends on how symmetric this is. If this curve is perfectly symmetric with this curve, then the average force would really be in the middle. And you could imagine cutting the cap off of this at the halfway point and taking this piece and flipping it around to fill in and making the little rectangle just like we did here. But it's hard for you to really know that. I mean, how can you really know just by looking at the graph that that curve is perfectly symmetric with that graph? So you could estimate it. You could estimate it and say, I'm just going to use F average times the delta t, and that would be pretty accurate. That's an estimate. Okay, that's an estimate. Or you might be asked to approximate. Okay, and in general, that's probably pretty accurate. However, a little more accurate way of doing it would be to look at something like this. When you look at the graph, you obviously will see grid lines. This method is tedious, to say the least, but probably a little bit more accurate and will take care of the situations where either the force is not symmetric, these two curves are not symmetric, or a situation where I just don't know. I don't know if it's symmetric or not. Then this method will be a little more certain to give me the correct value. Okay, and basically the way this works is you can see that we have boxes on the grid, and I could calculate this F times this T. That's just a simple rectangle, so I just use F delta T, and calculate the value, the area of one box. Now, in order for me to know the area underneath this curve, then what I would need to do is to know how many boxes do I have. Now, obviously, I can count up the number of whole boxes. Okay, so these are the number of whole boxes. And then from this point on, I need to figure out what part of the box that I have. So if I assume that each of these boxes represents one box, then I can look at these, and for example, I might say that this guy is 0.1 box. This guy is 0.7 boxes. This guy is 0.75. Here's one that is 0.05. So I would go along the edge and figure out what part of a box that I have here, and then I would just simply count them up. First I would count up all the whole boxes, count up all these individual whole boxes, and then in my calculator just keep adding 0.1 plus 0.7 plus 0.75 plus 0.05 plus whatever I cut for these edges. And then the way that I would calculate it is I would take the number of boxes and I would multiply by the area of one box. It's tedious, but it's probably more accurate and more certain than just saying that the midpoint, that the halfway between the maximum and the origin, is the average force, which may be true, but not really sure if it is or not. And obviously, some of the boxes you may overestimate, but you have to figure that some boxes you'll overestimate, some boxes you'll underestimate, and then overall, that the number of overestimates will kind of be balanced by the number of underestimates, and you probably will come up with a number that's pretty close to the real number. And again, you're not being asked to calculate, solve, or determine the value of the impulse. You're just being asked to approximate the value of the impulse. So that's like a really important thing to think about. So we're going to go away from this problem. I have seen it on exams before. That's completely legitimate for them to ask you this question. It would probably be a fairly high value question, like 3 or 4 points. But let's go back to the simpler situation and look at what would they do with this problem? Like, what will be the follow-up question? Because it's very unlikely that you're going to see a question in which all they simply ask you to do is to find the impulse of a particular graph, or the graph of a particular object. There's no point to that. So, give you an example problem in which we can use that information to figure out something a little more complex. So in this figure, the shows a force that's acting on a 0.41 kilogram ball, so maybe a slightly smaller than normal soccer ball, as it's being kicked. If the ball was moving towards the player at 5 meters per second, you're being asked to determine the final velocity of the ball after it's being kicked. Let's assume that the ball is kicked away from the player. So obviously, one of the things that we're going to want to do is to calculate the area of this thing. That will not give me the velocity, but it will give me the impulse, and obviously we know that F delta t is equal to m delta v. Okay, so this is where the problem is going. I'm going to use the impulse from the graph to figure out the change in the velocity of the ball, and therefore I'll know the final velocity of the ball. So in this situation, I'm just going to draw a little diagram to help visualize it. A ball is going to come in at 5 meters per second. This is my initial velocity. The ball gets kicked, it goes out with some new velocity, which I don't know the value of right now. Okay, so the first portion is pretty easy, right? Because it's just F delta t equals m delta v. Now, I could, right now at this moment, break up the delta v into v minus u. For the purposes of this problem, I'm going to hold off on that. I'm just going to calculate the delta v part because I just want to show you that there's it's a little tricky. You do have to be a little bit careful about the direction of these things because it could give you an answer that's completely bogus. So in this case, the maximum force, as you can see, is 60. Sorry, this is 1/2 F max. So because this is not a rectangle, we need to modify the formula a little bit. So it's 1/2 F max times delta t, which is 0.18 seconds. Okay, so that will give me the area of the triangle. And I do actually have the mass of the ball because they told me that it was 0.41. And then I'll get delta v. So the answer is 13.2. Okay, so now here comes the dilemma. If you think about the formula for delta v, the formula for delta v is v minus u. All right, now it would be really easy for me to say, okay, so this is 13, delta v is 13. I know u is 5. It says v minus u, so that tells me that I should add 5 to both sides, which would give me 18.2. And I'd get a final answer of 18.2. But that is a situation in which the ball is moving and then is kicked with additional force in the same direction. But that's not the situation that we're looking at. We're looking at a situation where the ball bounces backwards. So if you look at my diagram, you can see clearly that I've drawn the velocity 5 going in the negative direction. So this would be v minus negative 5, right? And that's easy enough. But then what about the delta v? Like, which way does the delta v point? Because I need to assign a direction to it. Do I automatically assume the delta v is in the positive direction? You can't do that. You can't assume that delta v is in the positive direction. You have to think about the situation as it goes. In this case, delta v does point in the positive direction because the ball was moving in this direction and then was kicked in such a way that it went in this direction. So delta v does point in the positive direction. And a really easy way to think about delta v and the way that delta v points is delta v points in the same direction as the force. The force in my diagram, in the way that I've drawn it, the force points to the right. The ball came in, it had a force exerted on it to the right, which brought it to a stop and sent it back in the opposite direction. So delta v points in the same direction as F. So for my situation, delta v is positive. Delta v does point to the right. It would be a positive value. This guy would be negative. And I would say that 13.2 equals v minus negative 5. So therefore, this would be v plus 5, and I would subtract it from the other side to get v is equal to 8.2 meters per second. Now, you don't have to be so formal. You could just reason it out. If the ball came in at 5 and the change in velocity was in the opposite direction at 13, then obviously I'm going to take away from the 13, I'm going to take away 5 meters per second. That would leave me 8 to travel off in this direction. So our final answer would be that v is equal to 8.2 meters per second. It's not a horribly complex problem, but just a couple of little things to really be careful of. That the area is being calculated using a formula that makes sense for that shape. If it's a triangle, if it's a trapezoid, whatever the shape is, you need a formula that's going to be modified to take that into account. And then secondly, even once you get that information, you have to be really careful about the delta V, because it would be easy to mess things up. So remember that delta V, right, because if you think about this equation, where does the directional information come from? It comes from these two guys. It doesn't come from T, and it doesn't come from M, and it definitely doesn't come from the 1/2. So the delta V, whatever the directional information for this guy, it has to be the same as the F. So in this case, if I wanted to plug in the V minus U right here, I would really need to think carefully about what was the direction of that force for my situation, as I have set up this situation so that it's consistent. So it's just one thing to be a little bit careful about, that issue of the direction. This is a really important thing to remember. Delta V and F point in the same direction.